Okay. On the program it says Timo Stripp will present this work in the ALMA project, but unfortunately he's not available today, so you have to stick with me today, but I think I can present it. Yeah. Okay, so I will talk about the ALMA European project. So what we did there, what the motivation is behind that, and show the results. Then I will focus a bit more on the matrix front end. So this is really the interface to the Scilab code. So this, I guess this is the more interesting topic for this conference. And then I will give a short overview about Matrix technologies. So it's something we will do with the results of the project. So what is the project? So the ALMA project is a European research project. So it was a 3-year project, or a bit more than 3 years. It was funded by the FP7 project, FP7 fund, and with a bit more than 3 million euros. And we at KIT were the coordinators of this project, so Timo Stripp is not available, but yeah. And we had 7 partners all around from Europe, so we had several universities here, KIT, University of Penn, and University of Peloponnese and Western Greece, so 2 from Greece, and some industrial partners like Recor, Intracom, and Fraunhofer IOSB. So first the question, why do we need multi-cores? So here's a picture of the development of Intel CPUs, and if we have a look at the green line, we can see, okay, this is something called Moore's Law. I guess many of you heard of it. So it's more like a guideline that every 2 years the number of transistors is doubled on a chip. But we can see here in 2005, or between 2000 and 2005, there is a bend in the other graphs. So the other graphs are something like clock speed and power, and we came to some physical limitations. So the chips weren't going faster by adding by higher frequencies or by adding some power, because it's not physically possible to overclock them anymore. They would get too hot, and it's just not possible. So the solution for that was to use multi-core processors now. So with multi-cores we have several cores, and they can work on the same problem more efficient because the chip is the load is better balanced on the chip. But for that, the parallelism must be exposed to from the programmer, and the programming such devices is a bit more complicated than a single core processor. So if we have a look at the motivation, so on the left side we have the end user perspective. So this is the programmer of a device, or not a device, this is a developer of an algorithm. So his main goal is just to develop or explore an algorithm. So he wants to use a simple, comfortable language and not care too much about the hardware. So he doesn't want to care about data types, about parallelism, so he just wants to focus on the algorithm and what it should do. So he's interested in the performance and energy efficiency of the program and how it's running on the device. But if we look at the target architecture perspective, or the hardware developers, we can see there are some problems. So they want to develop multiprocessor systems on chip with many features that are energy efficient, high performance, but how to program them. So they use explicit there are many ways. So one example is for explicit parallel programming. So and something like MPI, OpenMP. So the programmer has to explicitly say, okay, this part should run on core 1, this part should run on processor 2, or this whole loop should be split into 4 parallel threads or something like that. But if you program using such languages, you have to take care about everything, about many things yourself. So you have to think about what you're doing there. Then we have differences with a memory model, so MPI, message passing interface. Here we need some communication between the cores, so we have to explicitly send data from one core to the other. Another thing is where many processors now have single instruction, multiple data capabilities. So SIMD, so the idea here is that large amounts of data can be calculated with only small instructions. But this is also something that has to be done explicitly if the compiler can't do it itself. So this is something the compiler can't do always, but only in certain cases. And hardware architectures usually only support a specific only specific data type. So processors are usually 32-bit or 64-bit. So a 32-bit integer data type is a basic data type that's used in many architectures. So I'm focusing mainly on embedded systems here. So floating point performance is usually a problem on these architectures because there is not enough hardware available. So we can see there is some conflict here in these motivations of the end users and the hardware developers. And the idea of the ALMA project now is to hide the complexity of the hardware from the end user so that he doesn't need to care about the hardware architecture. So this is the basic ALMA development flow. We can see on the left upper side, okay, here we have the algorithm programmer, the developer. So he writes his algorithm just using Scilab, and he can use some annotations just to give some hints to the tools. On the other side, here on the right, we have an ADL, abstract hardware description. So here, this is also something we developed within the project. It's an abstract description of the hardware that defines all the needed information. So there are stuff like network on chip or communication infrastructure that is there, the memory hierarchies, but also the simulation aspects or some for the instructions that are executed. So how long does a 32-bit integer multiplication take and stuff like that. So these are the two input files we need for our ALMA algorithm parallelization tools. Then this tool does the automatic parallelization, and what we get out of the tool is a parallel C code that can then be used on the target platforms. So within ALMA, we used a processor from Recore, and KIT had another research processor that is not available commercially, or that is not available outside the KIT. And this code can then be either run on the platform or in the simulator. And we can see we have here some feedback optimization. So this whole process is done automatically using some simulation passes to get the best performance out of it in the different iteration steps. So now what is the challenge when we use Scilab, when we want to use Scilab on the multi-processor system on chips? So the Scilab is intended to be easy to program, to develop your algorithm. So it's just a sequential imperative language, so you can't really express any parallelism in it. Then you have many dynamic things which also complicate the translation. So dynamic typing means that you don't have to really care about the data type of the variables you're using. So if you have a scalar in Scilab, everything is a matrix. So if you assign some matrix value to it, it will become a matrix. If you only assign scalar values, it will be a scalar. It will remain a scalar. So there are some problems. So you don't have to define the real data type here or the real shape within Scilab. And so the basic data type is even floating point data type. So this is not the best data type when targeting embedded systems. And there are other things, so pointer free, so there are no pointers supported in Scilab, so it's something one wants to use if you program in C, but you don't really need it, so in Scilab it's just not possible. So now when we target the multiprocessor system on chips, we want to use two different kinds of parallelism. One is the task level parallelism, and the other one is the instruction level parallelism. So these are now the challenges we need to face when creating the code. bit about the target architecture of ALMA. So this is the commercially available hardware architectures from Recore Systems, X 2014. So one of the major points here is that we're targeting distributed memory systems. So there is no shared memory between the cores, or it's not required. So many parallelization tools target shared memory systems. But if we look at the future and target many core systems, we think that distributed memory, or at least not fully shared memories, will be the future. So we are targeting here already a distributed memory system. And we don't have any floating point units, so we need to create some fixed point data types. The architecture here is a tile-based architecture, so we have 6 computing tiles. We have a general purpose processor to control everything, and all computing elements are connected with a network on chip here. So, what are the test cases? We evaluated our approach in ALMA. So, one is from telecommunications, so this is from Intracom Telecom. It's from the WiMAX standard. You can see there's a long chain of different transformations. So the basic idea here is that data is encoded for transmission over the WiMAX, using the WiMAX standard. So we have some FFT here, we have some randomizer, and we have several things to create the frames. So what we could reach with the toolchain is a speed of 2.8 here. So you can see the green color in the lower, with the green we show when processors are working, yellow means they are waiting. So the toolchain here automatically can parallelize the application for 4 cores as far as possible. So in the later parts we can just let the processors run on the data. At the beginning, some pre-calculations have to be done, so there is no parallelism we could exploit here, but nonetheless, the speed up is not that bad. The next test application was from image processing, so it's from Fraunhofer IOSP. So it's the so-called SIFT algorithm. This is a feature detection algorithm that tries to find objects within a moving image or video, and it's split into 2 steps. So first we have to extract the features. So this is the description of the object we want to find inside the video, and then we have a matching phase where we want to find the object in the video. So here we could reach a speed of 1.8 using 2 cores. With 4 cores, we are also at about 2.8. So we can exploit a lot of parallelism we find inside these algorithms. But here we have some red parts in this execution. So here these red parts are also waiting cycles, so it's not possible to parallelize these algorithms completely. So this is a usual case that it's not green everywhere. The blue parts here are for data communication, so there is communication between the cores. It's not just a simple parallelization. What we also focused on was the reduction of the development effort. So we just asked the developers to compare the time they needed to develop for the multi-core systems manually and using the automatic toolchain. We can see for Intracom, they saved 57% of the time. So using the toolchain saved them a lot of time. Doing it manually is quite time consuming because there was a lot of debugging necessary. They had to think about fixed point data types and stuff like that. So they could save a lot of time. For the image processing, the fixed point data types were unfortunately not precise enough. That's why we couldn't save too much time there, but we can also speed up the process about 30%. So we can see this approach can save about 50% of time in the development time. So if we just have a look at the workflow, how to use this ALMA toolchain. So the basic idea is we have the programmer here on the left side. He develops his algorithm using Scilab. then he just gives this Scilab code directly to our ALMA parallelization toolchains, which could automatically generate parallel C code that can be run on the testing PC, testing platform, or a simulator, wherever. So it's just basic C code, which is using the ADL information to fit the target architecture that is described there. But we can also have some additional development cycles. So directly from the parallelization tool, we can give the programmer some hints on which parts could be written differently, maybe to expose a bit more of parallelism. And the outer development cycle means we can use this information from the testing platforms to also improve either the implementation from the user, or we can also use it in the parallelization tools here. So now the parallelization tool is not one tool, so it's a tool chain. To make it easier, we just split it in two parts here now. One is the metrics front end, the other one is the parallelization back end, maybe you can call it. The matrix front end is the direct connection to the Scilab, and we generate from the Scilab code a sequential static C code with the aforementioned restrictions, and this C code is then used in the parallelization process to generate the parallel C code at the end. And now I want to talk a bit more about the metrics front end and what are the challenges we faced there and how we solved them. So the metrics front end is a Scilab 2C compiler. So it's the basic idea is just to pass the Scilab code and to generate the C code that can be used for the parallelization. So we have the limitations. So the main limitations here are that we want to analyze the generated C code. So it has to be a static memory allocation. We don't. The C code has to be static. So no malloc and dynamic memory allocation. We have to avoid pointers. So in theory, we could transform some of the Scilab structures to pointers, but that makes analyzing the C code very hard for the parallelization process. So we avoid pointers completely. And we also have some more features inside these metrics frontends. So to do some high-level optimization directly on the Scilab code, and to create some loop nests or remove loops. So I'll go into detail further in the next slide. Yeah, here's another summary of the requirements. So Scilab is the import language, so we want to support a well-defined subset. We are still working on how large the subset will be, so we want to support as much as possible at least. In addition to that, we want to allow some annotations. So these are just some comments in the Scilab language just to help or to guide the parallelization process. So here for type inference, we can add some annotations for data types. So for example, we can force it to use fixed point data type for the whole process, although that is not supported directly within Scilab. And some hints for parallelization. So if we want to have a specific part on a specific core, we can also do that with some pragma annotations inside the Scilab code. And yeah, one important thing here is that the annotated code is the valid Scilab or MATLAB, which we also support code. So these are just comments inside these languages. And the target language is basic ANSI C89 C code, and it has to be polyhedral analyzable. So polyhedral here means we have static control parts, which are usually for loops where the dependencies are not too hard, but where the dependencies can be analyzed statically. So we have to avoid pointers there. So this is one requirement to do one part of the parallelization, and it has to be a static code. So here, no dynamic memory allocation and runtime decisions. So one of the big problems is the type inference. So type usually consists of the data type and its shape, and we have split these this into 3 different separate passes. So first we do the shape inference, then the data type inference, and then the variable inference. So what does it mean? Shape, okay, a shape can be found quite easily in some cases. So S here is a vector of size 3 because only one dimension was written. Here the f variable is a scalar variable, so we can also write it as a 1-by-1 matrix, so to say. And S, if we just add a number to the vector, it still remains the same shape. So these are the easy cases. The type is not a problem here, but for a bigger problem is something like growing areas, for example. So if you have variable A, we assign 1 to it, and if we then access element 1, 5 of this scalar value, the Scilab makes a vector out of it, where the first and the last entry are now 1. So to make C code out of this, we limit it to where we have to know the maximum size of these variables. So this is quite important if we index the vectors using variables. So if we access this like this, so A 1, B, the maximum value of B has to be known. So this is in Scilab runtime decisions. In C, it would be not that we couldn't do it efficiently, because we would have to delete the array and create a new array. So if we target embedded systems, that's a too large overhead. We can't afford that. So to limit this, we have 2 solutions. We can see we have these MFE fixed size and MFE sized function here. So everything that starts with the MFE are functions that are just implemented for the matrix frontend. So this is also this is a function that is implemented. So it's set, you have to define the size of the variable inside this function then. So this is just an information you add to the Scilab code. This is an old writing, so it's not using the commentary function. So usually you should write a comment just instead of calling the function. Yeah, fixed size or MFE size. This is also something. So before accessing a variable, you can just define what the range of the access might be. Data type. So Scilab supports data type. So we can just name any variable a double, int 32, int 16, int 8, whatever you want. So in theory, you could do that, but in practice, you don't do it usually. So you can see here, this is A, uint 8. You can define it, and it is working. So if you assign to an 8-bit integer a 256, it will become a 0. So Scilab is taking care of that. But what happens now if you want to make C code out of it? So square root 1, okay, from 1 it's usually a double value. From square root from -1 is a complex double. So what is square root of A? So usually we should use the complex data type, but it's often not the case that the programmer wanted to use complex numbers. It also adds a large overhead in the C code because we need to use 64-bit for the data. So what we are doing here is we just assume it's a double value, but we add a warning on the console, and yeah, the user should specify the data type he wants to use. So if he wants to use a complex number, then he has to do it explicitly. In using Scilab, you can change the data type of variables at runtime. So you can just maybe it's not called cast in Scilab, but you can cast the variable to another data type at runtime if you want to. But this is something we can't support in C. So we we always use the largest data type, and in C code we transfer, we convert it there. This is something I talked about already. So the shape, maximum shape or maximum size of an array has to be known also at before runtime. So we needed to generate the C code. It's not possible to access to access an array with higher numbers than we defined already. So if we have the data types and the types correctly found in the Scilab code, then we do some optimization passes. So loopify is one of the passes. So here the basic idea is, okay, what's done in Scilab with using one line. Here it's only a function zeros 2.3. Okay, zeros is maybe a too easy example because that could be done easier in C. You can also do it for ones. So if we want to transform that to C code, we need some loop nests just to have this functionality. So here this optimization really looks at the necessary loops and tries to avoid unnecessary loops, which is not always possible. So here if we want to assign variables to a whole array or to parts of an array, we need at least 2 for loops if we have 2 dimensions. So because we had several loops, in the next pass we simplify it again. So in some cases it's easier, it can be analyzed that the for loop is not necessary at all because only one value is written to the array, or because the borders are just so small, then we just remove the for loops again. So these optimizations here show these results. So we have here the example, the SIFT algorithm, again from the image processing. You can see the Scilab code is only about 8,000 lines of code, and the C code we generate out of it is between 3,000 and 4,500 lines of code, so it gets a lot bigger. But the simplification here takes about 1/3 of the whole size, so we can really simplify several things here. Magic is just a magic square computation, which is only a few lines in Scilab. Using C, we need about 500 to 600, but also we can see the simplify is useful in all cases. ZIF and intracom are the only 2 real examples, and we can see intracom also the simplify is reducing it from more than 3,500 to 2,000 lines of code. So this is a really useful optimization. So with these results, this is now for a bit of advertisement. We want to, we from KIT decided that, okay, these results are working quite good. The need for the tool is there, and we want to create a startup company with this technology. So we will use the results and make products out of it. But for the product of Entrix, we need a bit more than what we have in ALMA. So we want to realize an interactive parallelization. So here, the main new thing added to the ALMA project is this part here. The parallelization decisions and the feedback generated from the algorithms will be closely interactive with the end user. So it's not a fully automatic tool chain. So the ALMA tool chain is fully automatic if you want it to be, but in some cases it's just useful to have additional information from the end user. So if he already knows, okay, this part could be parallelized to 4 cores or something like that, then it's just easier if he has the ability to do that. And we also want to help automatic test generation to just build more reliable code. The main idea is also to have a fully integrated workflow where you can develop your algorithm using Scilab, and it's planned to work also for Xcode, so for model-based design, not only Scilab scripts like now. And so the plans for the next So next plans for Mtrix. Currently, we have applied for a funding, so we are still waiting for result of that. Unfortunately, we get the result next week, so I can't say something definite right now. But we want to split the product into different parts. So what I told about the Matrix frontend, we plan to release it in the Atoms Scilab store, or Scilab framework. So this will be free to use, so you can generate static C code out of Scilab C code, out of Scilab code. And we want to launch the real product Mtrix Parallel Studio, or something like that, so it's not the final name, at the Embedded World 2016. So this will be fully integratable with the workflow, and we want to support different hardware platforms and model-based design. Probably not all on February, but it's the long-term plan. So to sum it up, yeah, I've talked about the ALMA toolchain and what it does with the Matrix frontend, the parallelization, and how we want to exploit these results using in a startup company called Mtrix Technologies. So thank you for your attention.